The universe we perceive is a grand deception of distance. We look out into the cosmic ocean and see islands of light, galaxies, nebulae, and stars, separated by gulfs of darkness so profound that traversing them would require journeys lasting millennia, even at the speed of light. This perception is built upon the assumption that space is a fixed, absolute stage on which events unfold. But a century ago, our understanding of the stage was irrevocably shattered. Albert Einstein's theory of general relativity revealed that space is not a rigid backdrop, but a dynamic, malleable fabric, interwoven with time itself. This space-time fabric is bent and warped by mass and energy. Planets, stars, and galaxies create deep gravitational wells in its surface, like bowling balls on a rubber sheet, forcing everything around them to follow curved paths. This is gravity, but if space-time can be bent, a far more radical question arises, one that pulls at the very seams of reality. Can it be torn, folded, and stitched back together? The answer, born from the dense mathematics of Einstein's own equations, is a tentative and tantalizing yes. Imagine the universe not as a flat sheet, but as a vast piece of paper. To get from one point on the paper to another, an ant must crawl the entire distance. But if one were to fold the paper, bringing the 2 points directly together, the ant could simply step across the fold, completing its journey in an instant. This simple analogy is the heart of a wormhole, a theoretical tunnel or shortcut through the fabric of spacetime. It is a bridge connecting two vastly different regions of the cosmos, or perhaps even two different moments in time. Such a structure is not the idle fantasy of fiction, but a valid mathematical solution to the laws of physics that govern our universe. The first of these solutions, known as the Einstein-Rosen bridge, emerged from the study of the most extreme objects in existence: black holes. The Einstein-Rosen bridge describes a scenario where the singularity of a black hole in one location is connected to the singularity of a hypothetical white hole somewhere else. A white hole, the mathematical time reversal of a black hole, is a region of spacetime from which matter and light can only exit, never enter. In this model, the two singularities are connected by a throat, creating a potential pathway. To an outside observer, one would see the inescapable gravitational pull of a black hole, but falling into it would not lead to annihilation at a single point. Instead, it would lead into the throat of the wormhole, and, in theory, out of the white hole's explosive expulsion in another part of the universe. For a fleeting moment, a gateway to the stars seemed to be a natural consequence of gravity. However, the universe is rarely so generous. Further analysis revealed a cruel and fatal flaw in this elegant construction. The bridge is ephemeral, a ghost of a passage. The throat of an Einstein-Rosen bridge would pinch off and collapse under its own unfathomable gravitational stress, with such speed that not even a single photon would have time to traverse it. Any object attempting the journey would be crushed at the singularity as the gateway slammed shut. The cosmic shortcut was a dead end. To build a stable, traversable wormhole, something else would be needed: a cosmic scaffold made of a substance that could defy gravity itself. The problem of gravitational collapse, then, presents a seemingly insurmountable barrier. To construct a bridge across spacetime requires not just bending the fabric of reality, but actively holding it open against its own immense, self-crushing weight. The quest for a traversable wormhole thus becomes a search for a substance with properties so counterintuitive that they border on the magical. It would require a material that generates a form of anti-gravity. Normal matter, with its positive energy and mass, curves spacetime inward, creating the gravitational attraction that pulls everything together. To counteract this, a wormhole's throat must be threaded with something that possesses negative energy density. This exotic matter would curve spacetime outward, generating a repulsive gravitational force that would push the walls of the tunnel apart, stabilizing it against collapse. This concept is not mere speculation. It is a requirement dictated by the laws of general relativity. To prop open a gateway through spacetime, one needs a substance that weighs less than nothing. This exotic matter would have bizarre properties. It would be gravitationally repulsive to everything around it, and shining a light on it might cause it to move away from the light source rather than being pushed by it. It is crucial to distinguish this from antimatter, which, while opposite to normal matter in charge, still possesses positive energy and would gravitate attractively just like anything else. The need for this substance pushes the boundaries of known physics, yet it is not entirely without precedent. A quantum phenomenon known as the Casimir effect demonstrates that, under specific conditions, the energy density in the space between two closely spaced, uncharged conductive plates can be lower than the energy of the vacuum outside them. This is a real, experimentally verified instance of negative energy density. However, the Casimir effect produces this result on a microscopic scale and in minuscule amounts. The engineering challenge would be to find a way to produce and control a vast, stable quantity of exotic matter, perhaps on the scale of a planet's mass, to stabilize a wormhole large enough for a person or a spacecraft. No known physical process allows for this, placing the artificial construction of wormholes firmly in the realm of hyper-advanced, theoretical civilizations. Yet, if such a substance could be harnessed, the nature of the wormhole would transform entirely. It would no longer be an inescapable trap like a black hole. Without an event horizon, the point of no return, one could theoretically approach the mouth of the wormhole, peer through its shimmering, distorted aperture to the distant location it connects to, and then safely retreat. The view through the portal would be unlike anything else, a spherical window onto another part of the cosmos, with the starlight from the other side warped and bent as if seen through a celestial crystal ball. The journey through its throat would be a passage not through solid walls, but through a corridor of pure, stabilized geometry. The stability problem might be theoretically solvable, but in doing so, physics uncovers an even more profound and dangerous possibility. If one can connect 2 points in space, what is to stop one from connecting 2 points in time? The ability to connect 2 distant points in space is already a profound concept, but it is merely a prelude to a far more unsettling consequence. The very theory that allows for the bending of space, relativity, also dictates that time is not absolute. Time flows at different rates for observers in different gravitational fields or moving at different speeds. This phenomenon, known as time dilation, is not theoretical. It is a measurable reality, accounted for every day by the GPS satellites orbiting our planet. When this proven fact of reality is combined with a traversable wormhole, the combination creates a gateway not just through space, but through time itself. The construction of a time machine becomes, alarmingly, a straightforward engineering problem, assuming one could first master the creation of a stable wormhole. Imagine 2 mouths of a wormhole, A and B, created in a laboratory, initially at rest, and synchronized in time. If mouth B is placed on a starship and taken on a round trip at near the speed of light, for what observers at mouth A perceive as 1 year, time dilation would take effect. For the traveling mouth B, less time would have passed. When the starship returns and mouth B is placed at rest next to mouth A again, their clocks will be out of sync. The clock at mouth A might read the year 2050, while the clock at mouth B reads only 2041. A stable tunnel now exists where the entrance is in 1 year and the exit is 9 years in the past. Stepping from A to B would be a journey backward in time. Stepping from B to A would be a leap into the future. This immediately opens a Pandora's box of logical contradictions that threaten the very fabric of causality. The most famous of these is the grandfather paradox. A traveler could, in principle, use the wormhole to journey into the past and prevent their own grandparents from ever meeting. If they succeed, the traveler would never have been born. But if they were never born, they could not have existed to make the journey into the past in the first place. The sequence of events creates an impossible, self-negating loop where cause and effect become meaningless. This is not just a philosophical puzzle. It represents a fundamental breakdown of the logical consistency of the universe. Faced with this intolerable possibility, physics seems to have devised its own defense mechanism. The late physicist Stephen Hawking proposed the chronology protection conjecture, which posits that the laws of physics themselves conspire to prevent time travel on a macroscopic scale. The conjecture does not forbid wormholes, but it prevents them from being used as time machines. One leading hypothesis for how this cosmic censorship might work involves the amplification of vacuum fluctuations. As a wormhole's mouths are manipulated in a way that would create a time loop, a feedback circuit is created for virtual particles that perpetually pop in and out of existence in empty space. These particles could travel through the wormhole into their own past, interact with their earlier selves, and re-enter the wormhole, creating an endless reinforcing cycle. This feedback loop would cause the energy density at the throat of the wormhole to skyrocket towards infinity, generating a blast of radiation that would violently destroy the bridge at the precise moment it was about to violate causality. The universe, it seems, would rather self-destruct a pathway than allow its own history to be rewritten. But is this violent self-correction the only possibility? Or does reality have a more elegant solution to the paradox of time? While the explosive self-destruction of a nascent time machine provides a dramatic and effective safeguard for causality, it may not be the only way the universe handles such a potential crisis. Reality might employ a far more subtle and elegant form of self-regulation. One such possibility is the Novikov self-consistency principle, which proposes that while time travel to the past may be possible, changing the past is not. The principle asserts that there is only one self-consistent timeline. Any action a time traveler takes in the past was always part of that history, and in fact, was part of the chain of events that led to them traveling back in time in the first place. The probability of an event that could create a paradox is, in this view, zero. You cannot go back and kill your grandfather because the laws of physics would simply not allow it. Your gun might jam, you might have a sudden change of heart, you might slip on a misplaced object. More profoundly, your journey to the past was already woven into the tapestry of events. Perhaps your appearance was the very catalyst that caused your grandparents to meet. In this deterministic view, free will is an illusion. History is a closed, immutable loop, and a time traveler is not an editor of history, but merely an actor playing a pre-written part. An even more exotic alternative arises from the strange world of quantum mechanics, the many worlds interpretation. This theory suggests that every quantum measurement, every decision point, causes reality to split into multiple parallel universes. In this context, a time traveler's actions don't create a paradox because they don't alter their own timeline of origin. If a traveler journeys to the past and prevents their grandparents from meeting, they have not erased their own existence. Instead, their action has caused a new timeline to branch off from the moment of their intervention. In this new, alternate universe, they will never be born. Their original universe, however, remains completely unchanged, unaffected by their departure. The time traveler becomes an exile, a refugee from another reality, now stranded in a parallel world of their own making. The grandfather paradox is resolved because the man who was prevented from meeting his spouse is not, in a strict sense, the traveler's own grandfather, but rather an alternate version of him. Causality is preserved within each individual timeline, at the cost of an infinite and ever-growing number of parallel realities. Thus, the wormhole stands as a profound nexus where the grandest theories of physics collide with the deepest philosophical questions. It remains a purely theoretical construct, a ghost haunting the equations of general relativity. The physical requirements, chiefly the harnessing of vast quantities of exotic matter, place them far beyond any foreseeable human capability. Yet, they serve as an ultimate thought experiment, forcing us to question the nature of space, the linearity of time, and the very structure of reality. Are they real physical possibilities, natural tunnels in the quantum foam of space-time, waiting to be discovered? Are they potential artifacts for a civilization millions of years beyond our own? Or are they simply a mathematical siren song, an elegant fiction that reveals the limits of our current understanding? The answers remain locked away, perhaps forever, in the fundamental workings of the cosmos. But the pursuit of those answers expands the human imagination, reminding us that the universe is not only stranger than we imagine, but stranger than we can imagine.